So I just start off with a small appetizer. So here, subtracted two 3D seismic volumes from each other, and you see a very clear brightening in amplitudes, which you could say is a 4D effect from production. But of course, one of the things, the problem here is that because of production effects, you have time shift, so it doesn't really tell you anything directly about what is happening in the reservoir. So the first step here is to try and remove these time shifts from the seismic data. And that's what I've done on this slide here. So now you see a much more subtle, but certainly also more realistic 4D seismic difference, which we can use to tell us something about what's happening in the reservoir. We'll then invert these differences in amplitudes from the different surveys. And here you have from monitor to baseline, the change in VP/VS. And you see again, very clear brightening around the two reservoirs intervals we have in this example. Then taking a rock physics model, we can then convert it into a change in water saturation. So now you see that the lower reservoir has a very clear change in water saturation, and the upper reservoir intervals are slightly less. If I then compare with where I started a minute ago, we have all the brightening on the left-hand side. We are talking about amplitudes, we are talking about reflectivity, and now we have the water saturation directly on the right-hand side. So maybe here we're talking about changes in amplitude of 10–20%. Of course, important information. But when I'm finished with the 4D inversion, I can now talk about what the reservoir engineer want to learn more about: change in saturation. So the green color here is a change in water saturation of 15%. The blue color is around 10%. So it's really this step from talking about geophysics, so reflectivity or amplitudes, to talking about dynamic reservoir properties from the seismic data I want to present to you today. So to look at the 4D quantitative process that we will go through, first of all, we'll look at the 4D time shift estimation. Very, very critical to this whole process. And from that, we get two volumes. We get a 4D normalized RMS amplitude volume. So that tells us something about the change in amplitude from one survey to the next. And then we get a 4D time shift volume, and that tells us about how we need to align the different surveys due to the production effects. When that's been done, we can then perform the 4D simultaneous AVO inversion, and we invert directly for the differences from vintage to vintage. And the result of that is changes in acoustic impedance over time, and changes in VP/VS, and even sometimes in density. With these results, we can go to the next step, and that's the rock physics inversion using a rock physics model. And we can then calculate the changes in water saturation, gas saturation, porosity, and sometimes even the effective stress. If we look at this more like a workflow, we start, of course, at the top, where we can take as many seismic vintages as you like, as many angle stacks for each vintage, and as many azimuth for each vintage as well. So the first step here would be, again, to remove the time shift, make sure all the data is properly aligned. We can then continue to the actual 4D simultaneous AVO inversion, and that's where we will estimate wavelets, so matching the well logs up against each of the angle stacks, and we'll also derive low frequency models to compensate, or 3D low frequency models to compensate for the information not available, low frequency information not available in the seismic data, and that goes for the 4D as well if the production effect is sufficiently significant. Then the result of the 4D inversion is 3D inversion results for one vintage. So that gives us sort of the framework, the background, acoustic impedance, the VP/VS, and in many cases also the density. And then we get a second set of parameters, which we inverted for directly, and that's the changes in acoustic impedance, the change in VP/VS, and the changes in density. We'll then perform a rock physics inversion, and we'll develop a rock physics model to do that. And then the results of that is, again, a 3D rock physics result, sort of giving us the framework. So what was the original water saturation, what is the original porosity and V-clay. And we also get the 4D rock physics results, so changes in saturation, effective stress, and porosity. So that's the workflow we have to go through. In this presentation, I will not focus on all these parts. I will show you some examples of the time shift calculations, because they are very, very critical. I will show you some 4D inversion results, and I'll show you some 4D rock physics results. And really what I'll have focus on is the validation and the application of all these results. So a key part of this process that I have not included in today's presentation is the whole rock physics model building and rock physics inversion. And then if we look at this on the left-hand side, it's really a linear workflow going from the top to the bottom. But that's actually not how we are working. It's more an iterative workflow. So many of the steps we go through in this entire process will take the inversion all the way through to the end. So we get inversion results that we can compare directly with the well-log data. And in that way, validate each step we've done in the processing sequence. And the reason why that is doable is that all this is done in a scripting environment where it's very easy for us to either change parameters or input data and then rerun the process. The only real bottleneck in this process is if we have available compute power. The 4D inversion is a fully simultaneous AVO inversion using a 3-term Ecke-Richards. It's a nonlinear, globally optimized process. It's multi-trace, so traces are to some extent linked together, and we don't use any correlation functions between the different elastic properties that we're estimating. We can take an arbitrary number of input data, so for azimuth, angle stacks, and vintages. So if we had 4 azimuth, 5 angle stacks, 5 vintages, that would actually give us 100 volumes of 3D seismic data what we can process. And another critical part in all this is that we invert directly for changes both in the static and the dynamic reservoir properties. It's not just a simple subtraction of elastic properties, for example, from one vintage to the next vintage. I will show you some examples from 3 different projects today. So I'll start off with the chalk field South Arne, close to my home here in Denmark, then move on to Equatorial Guinea to the Siba and Okome field, and then finish off with the Athabasca oil sands in Canada. So 3 fairly different types of projects and different types of results. So start with the first project, that's the South Arne field in Denmark. We have 4 surveys, 3D surveys, so a 99 baseline, and you end up with the 2014 OBS. So you can imagine the difference in quality from 95 streamer survey to an OBS in 2014 is quite large. So some of that differences in resolution, that's one of the things we will reconcile through this 4D inversion process. The development history of the field, discovered in 69 by DUC. Probably most people better know the main partner in that, and that was Maersk Oil and Gas. First production in 94, and then acquired by Hess in 94, and first production in 99. So we have 3 monitor surveys after the production. The South Arne field is a chalk field with 20 to 45% porosity, but unfortunately a very low probability, so the recovery rate is quite low. The dry mechanism here is depletion with some compaction, and you'll see also in some of the slides later water injection. What was of interest here in connection with the 4D project was to look at the reservoir compaction and the reservoir modeling. I won't really go into the reservoir compaction in this presentation, but more looking at how the results were used as part of the reservoir modeling. And really the target here is, this was marginal reserves that was being targeted, so how best to place infill wells and additional drilling for this particular field. So go back to some of the slides I showed you in the beginning. So we have here again the 4D seismic differences. And as I said before, there's no time shifts removed from this. So due to production effect, the different vintages have not really been aligned. So that is what we want to do with our seismic warping, as we call it. So what we do here is that we align the amplitudes from different vintages. And we do that both in the inline direction, in the crossline direction, and in the two-way travel time direction. And besides aligning the data much better through this process, we also reduce the acquisition noise and footprint. So if we look at the warping at one well location, on the left-hand side, you have the original two traces we're trying to align. Then you have the warp traces in the middle, and then you have the displacement curve in two-way travel time to the right. I'll try and zoom in a little bit so you can better see what's going on. So again, the original traces on the left-hand side, and then you see how everything has been adjusted with the warp traces, so peak to peak and trough to trough are more or less perfectly aligned. And that alignment gives us two sets of data. So it gives us the time shift volume, the delta TVT, as you see, and also when the data have been aligned, we can also look at the delta amplitude from one survey to the next, which will tell you something about what's happening in the actual reservoir as part of production. This is how it looks for the 4D time shift in milliseconds. So here you see it's from about 4 to 6 milliseconds over the central crest of the field. So fairly significant time shift had to be applied. Should also say here there's a gas chimney that certainly complicates things a little bit as well. And again, if we look at the warping in the inline direction, we see the displacement now in bins. So again, here is about 20–30% of the bin size that we have to move the data around on one of the flanks of the field. And in the crossline direction, you see it's very minor and it's sort of hovering around 0. So not very dramatic. But the significance of all this is that we go from the plot on the left-hand side, where we have a lot of brightening, to a much more subtle and realistic brightening due to the production effects on the right-hand side. Then running this on a full volume, we can now look at the normalized RMS amplitude maps. So on the left-hand side, you have it for the Ecofisk formation, and on the right-hand side on the TOR formation. They're on top of each other. You see the central part of the platform is down in the lower right-hand corner of both plots, and the red lines, the red well trajectories are the production wells, and the blue ones are the injection wells. The gray area, that's an area where there's a gas chimney, so the seismic data is not of sufficient quality to really analyze the results. And again, here you now see that the change in amplitudes over time are quite significant, especially for the TOR formation, and it's really centralized around one of the injection wells. Again, we expect this is part of changing the saturation, and this is an injection well, so that makes good sense. Then running through the inversion process, building the rock physics model, we can then say something about the change in saturation for these two intervals, again for the Ecofisk and for the TOR. Again, because the amplitude differences for the Ecofisk were fairly minor, the saturation change is also fairly minor. But you see for the TOR formation, it's quite significant saturation changes, and again seem to be related very much to where we have injection wells. So all these results are then used as part of the simulation model for this particular field. So this was the simulation model that was originally developed without using the 4D seismic inversion results. If we then go to the next, this is how the simulation model looks with the inclusion of the 4D inversion results. So if I just go back and forth, you see it's not dramatic differences, but again, remember, this was for infill drilling. This is marginal reserves, so even small changes can have a significant impact on where you actually locate a well. And this was used as part of the Ecofisk well planning. So you have the 4D normalized RMS amplitude map going from 2005 to 11. And if you see the very broad red line in the middle, that is one proposed well trajectory because it's in an area where there's no changes in amplitude over time. So essentially this could be bypass pay. Then we have the water change saturation for the same map. And again, you see the red line, that is where the proposed well is going to be drilled. And again, for water saturation, there's hardly any changes in water saturation here. So again, potentially missed pay. So before we were going up to from 2005 to 2011, now it's changing water saturation for 2011 to 2014. Now you see in the middle area, and I can just zoom in this middle area, there's much more changes in water saturation because a well was eventually drilled. And you also now see a saturation log that was run through the well, and you see that matches quite well with the saturation changes that we found from the 4D seismic data. So that was the first case study I wanted to show you. Then I'll move on to the Kumi and Siba field in Equatorial Guinea. Here we have 3 streamer surveys, 2003, 10, and 14, and 2 of them are monitor surveys. Again, the field was discovered in 01 and first production in 08. It's deep water turbidites with very high porosity, up to 30%. But really the critical part here is that the depletion is 30% annually. So this really requires quite an aggressive drilling and optimization for the reservoir to make sure you keep up production. And that was the background for this 4D project. The drive mechanism is depletion and some water injection. Here I'll show you some examples of how the results are validated. So here I'm just looking at validation of the basic 3D inversions. So this is from 2003. So what does the framework look at the beginning of production? So if we start at the left-hand side, we have acoustic impedance, VPVS, and density. The red curve is the well log. The blue curve is the inversion result at the well location, and the black curve is the low frequency model. So that is the guidance that we have put into the inversion. And you see that curve is fairly simple. So overall, for acoustic impedance, you see a very good match between the well log, again, the red curve, and the inversion result, the blue curve. If you go to the next column, the VPVS, you also there see quite a good match between the well log and the inversion result. And in this case, even density, not the same quality as the first two ones, but still quite a good correlation between the well log and the inversion result, which overall indicates this is very, very good high quality seismic data. Then the next 3 panels in color are the same results. So if I just look at acoustic impedance, you have the acoustic impedance log in the middle, and then you have the inversion result at the well location on either side. So it's just a different way of correlating the results. We can then move on and try and validate the 4D inversion results. Again, if we start at the left-hand side, porosity, and for the porosity curve, the curve on the left-hand side is the original well log curve, and then the right-hand side, that's the initial porosity estimation. So you see a good correlation between the two. The next column is V-clay, same thing. The inversion correlates well with the V-clay from the well log, but of course with less resolution. And then we come to the one that's really interesting, and that is the saturation log from the baseline. And again, here you see very high oscillations in the saturation log, but overall matching well with what we found in the inversion result. The next SW1 is then the production for monitor 1. So you definitely see there's been some production over the period of time. And then the SW2 is then for the next monitor survey, and there's not much difference compared to the previous monitor. A lot of wells were drilled here and were drilled as blind wells. So a quick assessment was done of how well are the seismic actually predicting the wells, how reliable are they. So of course, if we look at when did the seismic data predict a reservoir with hydrocarbons, and when was actually encountered in the reservoir, that's what we call the true positive, and that's what we want to find. But in some cases, maybe there's no reservoir, so that's our true negative. So there's no reservoir existing, and that was confirmed by the seismic data. Then we have the false positives and false negatives. Of course, those are the ones we want to avoid. We then look for the statistics for these 14 blind wells in total. You see that there is 10 true positives and one true negative. So in total, 11 out of the 14 wells turned out to have the correct prediction of the subsurface. So it both tells you something about the quality of the seismic data, that it has a very high ability to do the right predictions, and of course also tells you something about the quality of the inversion process. So this was used in the reservoir model. So here we're just looking at the acoustic impedance changes from the 4D inversion from 2003 to 2014. So the red area, just looking at the color scale first. So red is soft and blue is hard. So the red area, big red area, that's gas coming out of the solution. And then you see that the black arrow is pointing to the target area, and that's where we have quite a high impedance rock, which could be a potential target for infill drilling, just at the TD of the existing well. If we look at the original reservoir model before the 4D results were included, there was no indication of a presence of any hydrocarbon reservoir. But integrating the reservoir model with the 4D inversion result, now a reservoir target have actually been added. But maybe what's more of interest is looking at the VPVS changes. So here again we see a distinct anomaly, VPVS anomaly at the tip of the TD of the well, the existing well. None of that was present in the original reservoir model. But with the reservoir model being updated, we now see that there's a potential large target at the TD of the existing well. And these results were then used to impact the well workover for the field. So here we have the 4D inversion result with the oil saturation prediction. So you see at least 3 intervals where we have a high oil saturation. We have a big shallow layer and 2 smaller, deeper intervals. And then you see the well trajectory with the saturation log as well. And you see there's a good match with all 3 intervals. So good correlation between what the inversion found and what was found in the well. Then over to the last of the 3 case studies of today, the Athabasca oil sand from Canada. Here we have a baseline from 2006. After that, there was geophones permanently buried. And in 2015, then there was a monitor survey acquired, and that was approximately 6 months after steam injection on this field had started, and at a time when there was hardly any production taking place. There's 4 wells in the field, 3 with shear locks and 6 angle stacks. It's the McMurray Formation, northern eastern Alberta, as you see on the map. One of the key things here, of course, is this is high viscosity bitumen, so the oil is really difficult to move. So the 4D seismic, the objective of the project was to look at the production efficiency, look at well conformance, and try and understand the steam chamber efficiency. And as a result of that, potential targets, unheated areas could then be targeted for infill drilling. So just a few words on the SAGD, so the steam assisted gravity drainage. So as I said before, this is high viscosity bitumen, and that really impedes any natural flow. So the concept here, as you see on the drawing on the right-hand side, is that you inject steam above the bitumen. It lowers the viscosity, allows it to flow. It flows downwards into the producer, the producing well and can then be produced. And just one point, I said I wouldn't say anything about rock physics modeling. I will just show you this one slide. So one thing we found out here is that the conventional rock physics models were not really appropriate for the oil sands. Instead, bitumen had to be considered as a third solid along with quartz and clay. And using that, we could then estimate the end member minerals in the rock physics modeling. And then back to what I discussed earlier in the beginning about the warping. So again, here we have the 4D differences before warping. You see some nice, small, bright spots, but you also see some very high amplitude continuous events. After we then done the warping, you see a lot of the very bright amplitudes have completely disappeared. Now we know that the data is correctly aligned, so the differences are much more realistic to what's happening with the reservoir. And you see some nice small areas of brightening in amplitude, which could be related to the wells injecting the steam. So we can run the actual 4D inversion. So this is the acoustic impedance changes over time. And again, you see these spots where something is definitely going on as part of the steam injection. And we also have the VPVS changes over time. What we expect for when you inject steam and what happens to oil is that for the steam, the VPVS will actually drop. And for the bitumen, when it starts flowing, the VPVS will actually increase. So maybe that's some of the smaller red areas that you see below the blue areas. That is really the hydrocarbons or the oil that's starting to flow. Then taking the rock physics model, we can then look actually at the steam saturation changes. Again, you get a distinct feeling where the wells with the steam injection is actually located. And of course, we can look at the oil saturation change as well. You see the oil saturation changes are fairly minor. And that's, as I said, the production not really started. So what we're probably seeing here is just the first flow of the oil down towards the producing well, but nothing more than that. But we can look at this in 3D view, and we can see the steam saturation changes. Sorry about that. So you see the steam saturation changes, and again you get this feeling that you can see how the different wells with the steam injection are actually parallel to each other. And then we have the oil saturation changes, but again, remember these are very, very minor changes, and there could be some noise included in this result as well. And if you see them, it's exactly as you would expect, the steam on top, and then you have the oil starting to move below where you inject the steam. And just as final slide on the Athabasca oil sands is that if we just see where we started. We started on the left-hand side with just the differences in the seismic data, where all the brightening and amplitudes or the key brightening amplitudes don't really have any meaning. On the right-hand side, we can now directly talk about steam saturation changes. So we're going from reflectivity, amplitudes, to actually dynamic reservoir properties. From these three case studies, I hope you appreciate how we've gone from reflectivity, so again amplitudes, frequency bands, things like that, to direct reservoir properties. It could either be the static reservoir properties, but also the dynamic reservoir properties like gas saturation, steam saturation, and oil saturation. We find that it is really critical to combine the 4D amplitudes and time shifts. So the time shifts we use to align the data, and the time shifts with the 4D amplitude changes tells us a lot about what's happening in the reservoir, again to tell us, to estimate our dynamic reservoir properties. This is also a very powerful way of integrating geophysics, geology, and reservoir engineering. So again, a lot of our input are geophysics from the seismic data, geology from interpretation of well logs, but we really end up with with reservoir engineering properties, the information that the engineer would really want for the reservoir model or for the simulation model. Then the final thing we found with this type of project is that we condense massive amounts of data into a very few reservoir properties. So if we imagine we had 4 vintages, 5 angle stats, 4 azimuth, I've then written it's more than 100 volumes. It's actually only 80 volumes, but just shows you so big numbers that you easily get confused. If you then in the field have maybe 10 wells, a minimum of 8 well log curves for each well, which I think is fairly realistic, you also have 80 sets of well log curves. So this is quite a lot of data, both to handle, but also how do you want to integrate it. But through the 4D inversion process, you could really condense this down to 5 calibrated volumes. So an initial porosity, initial saturation, and 3 delta oil saturation results. And when I say they're fully calibrated, by that I mean that through the whole process, everything has been matched up against the well log data. So we know